Any questions? Okay, so let's start. Yesterday, what we were discussing was Cooper problem, where what we have is a filled Fermi sea. This filled Fermi sea is non-interacting. And on top of this, you have two electrons that are interacting with each other. Now, what we are interested in is to calculate bound states, if any, for these two electrons. Now, keep in mind, yesterday somebody asked about hydrogen atoms. So you have looked at bound states earlier, but in the context of hydrogen atom, you solved a single particle problem. And you found out that you have various quantum numbers, n, l, and m, and you can label all the single particle eigenstates with these quantum numbers. So there are many bound states. Perhaps it was not surprising there you had a positive charge and one single electron that sees this attractive potential. Now it's a two-body problem. You have two electrons in attractive potential. The main difference is, of course, exchange statistics. Now you have to make sure if you exchange two electrons, because they are fermions, you should get a minus sign. They should be antisymmetric under exchange. Now, this two-body problem can be simplified further. So it's a two-body problem, two coordinates r1, r2. We can write this wave function. Let's go to the center of mass coordinate. This is an operator. The coordinates are operators. And the relative coordinate that I'm going to write just as r. The Hamiltonian for this two-body problem also has a center of mass part and a relative part. The center of mass part just has kinetic energy. This is something that you did also in the first tutorial. You looked at two electrons in a magnetic field. Or sorry, not electrons, two anyons in magnetic field. Now, this is the center of mass Hamiltonian. This you already know what to do with this. This is a free, essentially a free particle. So the wave functions in the center of mass coordinates are plane waves. The relative, this is the equation that we wrote down yesterday. H relative E. Okay, so we can also look at this further. What we are going to do is we are going to minimize energy in the center of mass coordinate. It will become very clear 10 minutes from now why. We don't have to, but we choose that the energy, that the center of mass has no momentum. So PCM is 0. So the center of mass momentum is 0. That means one electron has momentum k and the other one has momentum minus k. So it's h bar k is momentum of one electron, then the other electron must have momentum minus h bar k. Any questions so far? This is just an assumption. So there is no energy in the center of mass coordinate. Then you're left with solving this equation. H relative psi is the eigenvalue times the wave function. And we wrote down the eigenvalues in a special way. We wrote them as epsilon f 2 times epsilon f plus e. So let me put this r here. So we want to look at the eigenvalue such that E is negative. What does that mean? So we are looking for a bound state of a system. Both of these electrons will have momentum in excess of Fermi momentum. So one is k, other is minus k. You can think of this as, let's say this is your K, and then somewhere here is minus K. So the other electron is here. Both of these electrons have kinetic energy in excess of Fermi energy. Yet the total energy of this state is going to be lower than the Fermi energy, 2 times the Fermi energy. You can think of this as the attractive, you can think of this in the following way. The attractive potential in some way will cancel this excess kinetic energy. Now, if you had non-zero center of mass momentum, if the attraction is very weak, then the energy available from this attractive interaction might not be able to cancel this excess kinetic energy, because you will have more energy in the center of mass coordinate. So it is reasonable to assume that you have zero center of mass momentum. Again, this is in the weak coupling limit, or the attractive interactions being net attractive interactions being very small. Any questions so far? So we went through this algebra. You can write down the relative Hamiltonian. You have the kinetic energy in relative coordinate. There is a factor of 2 that you should be careful about. And just write down the equation and the attractive interactions. And then what we did is Fourier transform this equation. And that's where we stopped. So I'm going to write down the equation. So last time we deduced that this E minus, we define these variables psi k times psi k. This is sum over k prime, vkk prime, psi k prime, where this psi k is epsilon k minus the Fermi energy, where now this epsilon k is simply the free energy, the non-interacting free particle energy for a single electron with factor 2m minus epsilon f. So psi k essentially is measuring how much energy per electron in excess of EF you have. It's just redefining the variables. Any questions so far? So what we are going to do is we are going to simplify this problem further. We still have this potential vkk prime. In general, this can be a very complicated object. The way it depends on both the momentums. So we are going to make an approximation which is called on-shell approximation. What that means is we are going to consider a small shell around the Fermi energy. So this is Kf. And there is a small region of energy around Fermi energy. This is 2h bar omega c. This total width of the shell is 2h bar omega c. So we are going to assume that this potential is attractive only in a small window of energy around the Fermi energy. The motivation for this comes from the fact that we are going to assume that these attractive interactions are coming from phonons. Now, phonons have the energy scale corresponding to phonons is the Debye energy. And this Debye energy is typically much smaller than the Fermi energy. So the length scale over which this attraction is assumed to be relevant is, energy scale over which this attractive interaction is relevant is much smaller than the Fermi energy. And then we are going to ignore any feature that this potential may have and just going to keep the fact that this is attractive. Now let's put this in this equation. So this would imply that psi k is potential V where this star is a notation that means when I have sum with this asterisk, what this means is sum over all k prime values such that the energy is in the shell. So the point is outside the shell, V is just 0. So this sum over k prime, where V is non-zero, is only restricted to energy values inside the shell. So we only sum over k values that correspond to these energies. So this is the equation that we would like to solve. Now what we are going to do next is apply this operator sum over k on shell on both sides. So you can see sum over k and this will give us the eigenvalue equation. I think there might be a minus sign. So this is VKK prime. So I put minus V. So I should get a minus sign here. Or no. Sorry, no, I think it's okay. So the eigenvalue equation, you can check, this will come out to be 1 over V sum over k, all the on-shell values, 1 over 2 Any questions? So if we solve this equation, we can find out the values of E. So that is what we are going to do next. We want to find out values of this E. And in particular, we would like to find values of E that are negative, that will correspond to bound states. So one way to convince you that there is a bound state is to plot. So we want to solve this equation for E. We can plot both the left-hand side and the right-hand side as a function of E and see where they intersect. So that's what I'm going to do next. So let's plot this right-hand side. What does this mean? So this psi of k is this quantity. Now the sum over k over there, that means there are many terms on the right-hand side. Each term contains a k value so that you are in this shell, right? Now you have a filled Fermi sea. So even though we have a shell, the K values can only be larger than Kf. Below Kf, everything is filled. So the K values on this shell that are allowed are only larger than Kf. That means this quantity is larger than 0. That means 2 times psi k is greater than 0, but it can still take many values. So it can take its sum over many terms. The allowed values of k can be k1, k2, k3, many of those in the shell, but all of them are greater than kf. So you have many values of psi k, many terms on right hand side, and 2 times psi k is greater than 0. At all of these values, so I'm trying to plot these values. These are various 2 psi k values that are allowed. At all of these values, the denominator will vanish. So when E is equal to this value 2 psi k, we have a divergence. There is also one special value where it diverges, that is k equal to kf. When 2 times psi k is 0, then also right hand side will diverge. So you can check where the divergence is. So if energy is just above 2 times psi k, then the net expression should be negative. So I'm going to draw these lines here. These are 2 psi k values. So I can figure out that this must be going to minus infinity. It should go to infinity here, then minus infinity here, 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 here. So I will imagine that this looks like this. So in here, it can be some other function also. What about on the other side? So this is both, I'm plotting this equation, the left-hand side. So this is the right-hand side as a function of E. What happens on when E is negative? Well, again, there is a divergence. When E is just below 2 times psi k, it goes to positive infinity. So it should start from here. And after that, there is no other value of 2 psi k. And if E is minus infinity on this end, then it should really vanish. So the curve looks like this. This is plot of right-hand side of this equation as a function of energy. Any questions? Now let's plot the left-hand side. Left-hand side, now we assume the potential to be minus V, so V is a positive number. It's just a constant. So I'm going to draw. So there are many values of E that are greater than 0, but there must be one value of E that is less than 0. So this equation must have a bound state solution. Yes?
How do you know it diverges at E equals 0?
So I take the value K equal to Kf, which is also on shell, and h bar Kf square over 2m is defined as Fermi energy.
Okay.
So this EF is really h bar square Kf square over 2m. That's definition. We assume this. Any other questions? So now I have convinced you that there must be a bound state solution for this two-body problem. So next, we are going to find this. We are going to try to solve this analytically. So as with most things in condensed matter, it's good to convert the sums to an integral. So this sum over k, you can convert to an integral. So I'm just going to do this trick once more, and after that we'll assume that we can all do this. So we have d cube over k over 2 pi cube. And we are integrating on shell. Now, next it's useful to do is to insert a delta function. Insert a delta function, and let's call this some and integrate over this energy. Now only k dependence is in this delta function. Combine, now switch the order of integrals and use the definition of density of states. So what you'll be left with is this integral. Now in superconductivity, because rho is reserved for resistivity or resistance, it's very very common notation. We are going to use G for density of states. So this G gives you the density of states. And the integral is on shell, so minus h bar omega c to h bar omega c. So next we are going to assume that the density of states is constant or does not change over the length scale, over the energy scale of h bar omega c. So density of states is a function of energy. So from zero energy to all the allowed values of energy. This energy scale, 2h bar omega c, is very small compared to the Fermi energy. So in this window of integration, I'm going to replace density of state, which should be a function of psi, by one value, which is its value at the Fermi energy. So this is density of states at the Fermi energy times also, yes.
When you're converting the sum to an integral, should it not be multiplied by the volume?
So typically the way, I think if you had let me check. So K, it has, yeah, I think you're right. So K is over, yes. Yes, that makes sense because in density of state you have volume factor that will cancel with this. Thanks. So another thing that you can see that in this sum over K, we deduced that because we have filled Fermi C, only values K can take is greater than Kf. That means this integral really is from 0 to h bar omega c. Right? So for K greater than Kf, psi K is starting from Fermi energy and going up. So Fermi energy corresponds to 0 here. This. Now, we can do this integral easily. And what we will find is that this quantity here is the density of states at the Fermi energy divided by 2 and log So this is something we can rewrite, and we will get that this energy is 2 times h power omega c, 1 minus exponential 2 divided by density of states at the Fermi energy multiplied by this interaction potential V inverse. So that is the equation. 1 over V is equal to that. Just take exponential and go through one line of algebra, and you can write this energy to be this. So next, we are going to assume what is called we are going to work in what is called weak coupling limit. Any questions?
How do we know that that's negative?
Which one?
The energy.
We don't yet.
Okay.
I'm going to it in general for general V and tensive state functions. It's not. But now we are going to assume weak coupling limit. So it depends on exponential whether it's large or small. Yes.
So this just gives you one solution, right? But you can see from the line you've drawn that there are many solutions.
Yeah.
At what point did we, isolate one?
So here you can see there might be many solutions even for this equation, but we are really going to look at now the weak coupling limit. So far, okay, let me try to see. I think I understand your question. So what have we done? Okay, so one of the things we have done here is we are now no longer interested in this psi k stars anymore. So this is a transcendental equation. We can analytically find this solution, but all other solutions, as scattering solutions, are still difficult to find. So this method will not give you. So you really, I think in just one more, okay, I can answer it here. So if, say, V goes to 0, you can see that this expression is not analytic. So these solutions are harder to find. So you're right in the sense that if you're interested in finding other solutions, it's not an easy task, but this solution is particularly easy to find. Does that help? Yeah. So now this weak coupling limit, this basically means G epsilon F V is much smaller than 1. Now, if this quantity is much smaller than 1, this exponential is large, you can ignore this 1, and you can straight away see that the solution is negative. Yes?
G times V is a coupling constant.
So, in general, this V involves 2 electrons, so it's always useful to multiply this with density of state. So, essentially, if you are at lower energy, there will be lower number of K states available for occupation, and effectively you will have lower number of processes involved in this interaction. So it's just, it makes sense to define this as the relevant quantity. So in this limit, you can see that the energy is minus 2 h power omega c exponential minus 2 g e f v. Now, the other solutions where E is positive may also exist in this limit, but they are harder to find here. So it's easy to find the interesting solution, that is the bound state solution of this problem. Any questions? You don't look happy.
I'm confused because there it looks like you have like an infinite set of a discrete infinite set of solutions, and I don't see this discreteness on that thing. It's like kind of
No, so in this expression,
yeah, but how do you on the it's like okay, we did some assumptions. We have an expression for that.
also that discrete nature is somehow got buried into the integral, and the fact that we also assume that the energy density of state is constant. So I would not say that this is exactly same as the original one. And the reason we did that is because we're only interested in single solution below EF. So the information contained here and in that sum original equation is definitely not same. And the other thing is we are only interested in this around EF. That's the main. So even if there are many other solutions, what we are really interested in is just around zero. Now, the fact that this expression or the solution that we have found is not analytic at V equal to 0, this also means that this is a solution that you cannot obtain using perturbation theory. That was another reason why this problem took decades, why the theory of superconductivity was so elusive. That most methods that we knew, perturbation expansion, Green's function methods, all Dyson series, all the perturbative methods, they failed in this case simply because the solution is not analytic, and essentially what we had was a phase transition. Now, what this energy physically means, this is binding energy. So this is the energy, this is the amount of energy that the system can lower by forming pairs. So two electrons, they have their kinetic energy above EF. Both of them have energy above EF. They can pair up, and if they pair up, then they will lower down the energy by this quantity below EF. So the way we have written the eigenvalue, it's 2 times epsilon F plus E. So they will form pair, and they will emit, or they will lower down the system energy by this much. So now, if 2 electrons can do this, other 2 electrons will follow suit. They can lower down energy further, and then other 2 electrons can lower down energy further. Now, this process, imagine that it starts happening around KF, around the Fermi energy. Now, you start pairing electrons, lowering down system energy. So you lower down the Fermi energy itself. You take electrons from the Fermi surface, pair them. In this process, you're destroying the Fermi surface itself. Eventually, your energy, Fermi energy, will decrease because the electrons, Fermi energy is defined as all the single electrons, the highest energy, occupied energy of these single electrons. So you're taking single electrons, forming pairs. In the process, you're decreasing the Fermi energy. In the process, you're decreasing the density of states at the Fermi energy. Eventually, you will have this G of E going to 0. And when this is 0, again, E is 0. So the system has an instability if there is an attractive interaction, in the sense that you start with a system which has well-defined Fermi surface. If there are attractive interactions, this system is unstable. The system will pair up, it can lower down its energy, and in the process, you're destroying the Fermi surface. So the system is going through a phase transition. This process of lowering down energy or electrons pairing up will keep happening till you can lower down the energy. Eventually, the binding energy will be 0. So this energy is called binding energy. Eventually, this binding energy will be 0, and then this process will stop, and you have your new state that is very different from the state you started in. So this instability is triggered by the attractive interaction, and that is what causes a phase transition in these materials. Any questions? Yes.
Sorry, could you repeat what's the, like, so the system continues to pair up the electrons until what happens? What's the,
Till you can no longer reduce the energy, till the binding energy is zero. So this is the amount by which you can lower down the energy. Imagine if GEF is zero, then 1 over this, with this minus sign, is very large number. So the binding energy vanishes in that limit. So you pair up the system. In the process, you destroy the Fermi surface, you lower down the Fermi energy. Eventually, it will be shrink to zero, or it will go to a point where there are no states available, and then the binding energy will be zero. Now, this is a special case in the sense that we are assuming parabolic dispersion and everything. In reality, you will have block states, complicated, some messy band structure. Fermi surface might be complicated, but you can still go through this analysis. So the system will lower down its energy by pairing up till it can. Eventually, binding energy will be zero and it will stop. Any other questions? Yes.
Could you give an example? It's hard to imagine a density of states that has that is zero for some non-zero energy.
Yeah, it's hard, but we know from topology in some aspects, like sometimes you can have gaps. So imagine that you make transition from one band to other band. In that region, densive state would be zero in the band gap.
Right, okay.
So that would be one example. So next, what we want to do is, now we know that the system has this instability. Next, we want to develop a formalism so that we can write this new wave function. So now we want to write down a wave function that describes this new state. So how can we write down wave function of a single Cooper pair? So I'm writing down wave function for a single Cooper pair. So Cooper pair is, at the moment, from this analysis, our definition is a pair of electrons in the presence of Fermi C. So let's try to write down this state. We can write down this state in the following way. Where this F denotes Fermi C. So I have Fermi C, and on the Fermi C also, on top of that, I've created two particles, one with K up, other with minus K down. And the weight for this process, for this state, to create a pair of electrons with momentum K and minus K, such that their center of mass momentum is zero. For this process, the probability for creating such a pair is psi k square, mod psi k square. So this is sum over many terms. You can create a Cooper pair with any momentum k minus k. Also, we have encoded the fact that this is a singlet state, or the antisymmetry of the total wave function comes from the spin part, by restricting our pairs to have k up and minus k down. You can choose this down, this up, it doesn't really matter. But make sure we have a singlet state. Yes?
Is ket out the field Fermi C?
Yes. So this is the Fermi C.
So we don't start with any electrons.
No. But this is just one Cooper pair. And next, we want to write down the state of the superconductor, where all of the electrons have paired up. So if I want to write down a state where all of the electrons have paired up, let's assume there is total capital N number of electrons, and this number is even. So we are really talking about 10 to the power 23 electrons. So don't worry about whether this number is even or odd. This is a ridiculously large number. You may have odd, you may have 10 to the power 23 plus 1, that is unpaired, but that one single electron is not going to affect the physics. It will be dominated by 10 to the power 23 electrons, which we assume like some large even number. So let's, for simplicity, assume that the total number of electrons is even, and all of these electrons have paired up. So how would we write that state? So we can write that state as psi. Now this is for n for total number of electrons. Now I can create a Cooper pair. So I will have capital N by 2 Cooper pairs, but all of these capital N by 2 Cooper pairs have this wave function. And now I don't have fill Fermi, but I have vacuum. So I'm going to write it down and then explain what I mean by this. So just if there is any confusion, please ask. Our notation, this capital ket F is Fermi, this ket 0 is the true vacuum with no particles at all. So now what this state denotes is you can create capital N by 2 Cooper pairs, and each Cooper pair has this wave function where each Cooper pair can itself be created in any momentum state, any allowed value of k. So this is most general wave function for a system that contains capital N electrons and assuming that all of them pair up. So some of these psi k's will be 0. The probability of forming a Cooper pair in all k states is not identical. So some of these psi k's may be 0, some may be not. So we are considering a very general situation. Any questions? So so you really have, this is really a product, one term with sum over k. There will be n by 2 terms like this, and each has a sum over k or k1, k2, k3 till kn by. So there is a sum with some dummy variable k and n by 2 of these. So it's a really complicated object. To make things, or to, if you really want to get depressed, you can try to look at how many of these coefficients are there in this wave function. So let's try to estimate this. Let's assume there are m. Capital M is the number of k values. And from these many k values, you can choose capital N by 2 of these k values and create a Cooper pair with that value of k. Number of ways you can do this is m factorial Now, typically, this total number of k values, it depends on total number of ions. For example, if you are considering a periodic system, this is really of the order of 10 to the power 23. So if you assume m and n, the total number of electrons also of the same order, and try to estimate, use Stirling approximation, for example, to estimate what this number is, you'll find that this number is approximately 10 to the power 10 to the power 23. So this is how many coefficients we need to know to write down the state of the superconductor. Yes.
Under which assumptions are we assuming that the number of Cooper pairs is constant?
So at the moment, we are just assuming that all of them pair up, which means that the density of state is a smooth function. So there is always some finite bind. Yes.
Physically thinking, we are assuming that a system is at a finite temperature, right?
Yes.
So in principle, thermal fluctuations should be of order, thermal energy scale should be of order KT,
Yeah.
KBT, which we're not sure if it's larger or lesser than the binding energy we have here.
Yes. So let's set temperature to 0. So we can assume T to be 0. So there are no thermal fluctuations. So if I understand, you're saying thermal fluctuations can break up Cooper pairs, right? Yeah. So let's assume that let's do this calculation at 0 temperature for the moment. But you're right. If the thermal fluctuations, they can break up. The binding energy might be small, and so we are at 0 Kelvin.
Okay.
So at 0 Kelvin, the ground state still has these many coefficients. Now, this is ridiculously hard to calculate. So writing down the wave function in this way is simply not going to work for any practical purpose. So what BCS did is they said that let's go to a framework where the number of particles is not conserved. So essentially, this is going to grand canonical ensemble because it's such a large number, we can't really keep track. So let's go to the grand canonical ensemble where the number of particles is not fixed. But what we will impose is on average, this is fixed. So just like, so essentially, we'll now go to the grand canonical ensemble. So, and consider altogether different state. And I'm going to write down this state now. So now consider the state. Let's label it psi g. And this psi g is really exponential sum over k gk. Actually, let me use psi k. Sorry. Psi k, ck up dagger, c minus k down dagger on vacuum. Now, this is very different from this state. This really is a state that describes a system in grand canonical, or one of the states in the grand canonical ensemble. What does this state describe? So you can expand the exponential. You'll have the constant term that has no Cooper pairs. Then you have a term that has 1 Cooper pair. Then you have a term that has 2 Cooper pairs, then 3 Cooper pairs, and so on. So this is a state that is a superposition of all possible number of Cooper pairs. Yes.
These psi k is equal to those psi k's downstairs.
So they, at the moment, yes. Yep. So essentially, we are saying, I mean, there could be some renormalization of things depending on the total number, and here it's not fixed, but I think that will be insignificant.
Also, sorry,
Yeah.
this might be a mathematical detail, but shouldn't this state be outside the exponential?
You mean this, right? Yeah. Okay. Thanks. So what this state really does is it describes it's a superposition state of all possible numbers of Cooper pairs. Now you can write this state in another way. The sum over exponential, we will write this as a product over k exponential psi k ck up dagger C minus K down dagger on, again acting on vacuum. This again, now I will use the fact that C sigma square is 0, that the fact that these are fermions. Now this exponential, I can restrict it to only two terms. 1 plus psi k ck up dagger C minus K down dagger on 0. Any questions so far? So next, so this is now the state. This is state that we started with. Next, I'm going to rewrite this state in the following way. I'm going to write this as psi of g as product pi over all allowed k values uk plus vk c k up dagger c minus k down dagger acting on vacuum. Where mod uk square plus mod vk square is 1. So this is the form of the state that we'll work with. Instead of one variable psi k, we introduce another one and imposed a constraint that modulo square of these is 1. Why did we do this? In this notation, it is very clear. So if you look at 1, so this is a product over all allowed k values. Let's look at one term. In that one term, mod vk square gives you the probability that k up and minus k down are occupied. So the probability that you have a Cooper pair in state k, which is 2 electrons k up and minus k down, the probability is vk square, and mod uk square is the probability that you do not have these states occupied. So the probability that k up minus k down is unoccupied is uk. So in this product, if you have uk times 0, that will be unoccupied state, and so on. Yes?
Why can't we see that? Like going from here to here, it's like you've just, instead of 1, you're writing UK, and instead of
Yeah.
So like, it doesn't seem to me like these are the same thing. You know, like.
Well, so my goal was to motivate. This is the final thing we are working with. You could have just written this to start with.
Okay.
So if you're happy with this one, you can do. But the main point is, if you go through this, here it's in this way, it might not be as straightforward to see that you're in grand canonical ensemble. And in this way, it's more transparent to see that you're really, the number of, it's a term that has all possible number of Cooper pairs.
So then when you expanded the exponential in the last line there, is that just...
So here I assumed that the next term will have ck up square. So I just assume that the c square is 0 for fermions. So I did assume Fermi statistics here. Yeah. Yes.
If I understood well, these two expressions of psi j are equal to up to a normalization factor.
Yep. Yep. So there will be some problems using these states where you will show the normalization. So this equation ensures that the state is normalized, and these, I think it's in the tutorial on Tuesday. So next, we are going to use this state, and we have to do, the idea is to do variational calculation. So imagine that this is the state of the system, and imagine that UK and VK are variational parameters. So what BCS did is they started with this state, and they used the variational principle. They tried to minimize the Hamiltonian that they thought is relevant for superconductivity, and then they found out what UKs and VKs were, and then they knew the ground state of the superconductor. So this is what we are going to do next. For this computation, it's useful to write this state in yet another notation, which will make calculations much easier. So you can assume, so let's assume that 0, 0, okay, that's right, 0, 0, k, this is a state where both k up and minus k down are unoccupied. And 1, 1, k, this is a state where both k up and minus k down are occupied. So in this notation, what is vacuum? Vacuum is all possible k values should be unoccupied. So vacuum is simply product over all k, 0, 0, k. In this notation, you can write down this ground state as product over all k values, UK 0, 0, k plus VK 1, 1, k. Now, I think this is also either in the tutorial or in the homework problem. You can use this notation and you can show that this state is normalized. So actually, now that we are talking about this, I think another way to answer your question is going from here to here, I just wrote it in a way and imposed normalization condition. So we have product over k of mod UK square plus mod VK square. All of these are 1, so product over k values of 1. This state is normalized. You can calculate n bar, which is expectation value of the number operator. Now, when I write this, I mean expectation value in psi g, not in true vacuum. So let me clarify this. Okay. So this is psi g and psi g. If you calculate this, what is this number operator? This number operator is sum over k. The key point is that the spin values, okay, so this is what we are talking about when we calculate the number operator. The spin should come, up spin should come with k, and minus spin should come, the down spin should come with minus k. So this is the number operator. CK up dagger, CK up plus C minus K down dagger, C minus K down, and sum over all K. So if you calculate the average number, you will find that this is 2 times sum over K mod Vk square. If you calculate the average, the expectation value of n square, you will find that this is 4 times sum over K mod Vk square plus 4 times sum over K, K prime not equal to K, and when you calculate the fluctuations of n, this square, which is n minus n bar square, you find out that this is 4 times sum over K Vk square Uk square. Later on, when we will find our solutions for Uk square and Vk square, we will see that these fluctuations, they are high or they are large only in the vicinity of Fermi energy. So you can go through the algebra and show all of these, prove all of these expressions. So next we are going to do this variational calculation and find out what UKs and VKs are. So the next step is still to write down the Hamiltonian that is relevant for superconductivity. So this is called the pairing Hamiltonian, and let me just write it down. So this is sum over K sigma, epsilon K, Ck sigma, dagger, Ck sigma, plus sum over K, K prime, V, K prime, now, this is Hamiltonian. It's called pairing Hamiltonian. And what we are going to do is we are going to use this state and we are going to minimize that Hamiltonian. Now, the assumption here is that this Hamiltonian includes the term that is relevant for superconductivity. And this assumption, you can motivate A. If this assumption is wrong, the state that you will obtain by minimizing this Hamiltonian will not describe the superconducting state well experimentally. So all the experimental observations will not agree. So this is just an assumption. There are reasons why this might be a good assumption, which is to look at the spin indices. So this does have the right spin labels that could give rise to Cooper pair in the singlet state. This is really a much simpler term compared to what we have been dealing with. When we dealt with the Coulomb interactions or phonon-mediated electron-electron interactions, remember we started with 4 summing momentums. You can go to Fourier space. You still had 3 momentum sums. This term only has 2. So we assumed that Q is 0. We had K, K prime, Q. So I just want to say that this is a really simple Hamiltonian compared to the general form of interactions that we had. So we assumed that Q is 0. So there is no momentum exchange. Oh, well, there are only 2 momentums relevant in this scattering. So if you think of this as a diagram, you have K prime up minus K prime up and minus K prime down coming in. and K up and minus K down going out. Now, also what this assumes is that the incoming electrons, they had zero center of mass momentum, and the outgoing electrons also have zero center of mass momentum. So there is really no momentum exchange in the center. So it's a big assumption that there is no momentum exchange in the center of mass momentum. So what is really happening in this scattering is the center of mass momentum remains same for these two electrons, but the relative momentum changes. You have zero center of mass momentum going in, zero center of mass going out of the scattering process, but you can still change from K to K prime to K. And so this is, again, it's simplifying the problem a lot. This term by no means describes the most general two-body interaction. Any questions? If they are right, then this procedure will give us something useful. So next, we are in grand canonical ensemble. So we should minimize the grand canonical potential. So I don't know what notation used in thermodynamics. Let's just assume the grand canonical potential is E minus Ts minus mu n. So this is the grand canonical potential, this is the energy, temperature, entropy, chemical potential, number of particles. Now we are going to T equal to 0 do our calculation at absolute 0. And so this energy we are going to replace by the Hamiltonian operator. This term drops away. So we have to minimize H minus mu n. So this n, this H is operator, this n is operator, mu is chemical potential. At 0 temperature, it's same as Fermi energy. Any questions? So what does this mean? We have to minimize this quantity. So the first we do the variational calculation. So the variation should be 0. So what that means is I'm now going to write down these terms. Where I've defined, so I'm absorbing this chemical potential mu. So this number operator is same as this quantity. So I will absorb mu in this definition of psi k is epsilon k minus mu. Let's try to calculate this quantity here. So you have this operator, this annihilation operator, acting on this state, psi g here. So what I really have is, let me just write down a simple thing that will help in this calculation. So if you are looking at Ck sigma dagger Ck sigma acting on the ground state, let's write down the ground state as, let me just expand the whole thing. Let's write it down as U K1, 0, 0, K1 plus V K1, 1, 1, K1, and all K values. U, K, let's say large. Now, let's assume that there are M values, Km, 0, 0, Km, plus V, Km, 1, 1, Km. So you can see when this annihilation operator acts, it will do nothing to most of these states. It will only act on the state with K, where you have K1 to Km, one of these must be equal to K. It will only act on that state and it will pick out a factor Vk. So it can only destroy state that was occupied. So it will act on state somewhere here is a term that is UK 0, 0K plus VK 1, 1K. Somewhere here there is this term. This can only give you a finite answer if it acts on this term. And then you create a particle again, the one you destroyed. So you will actually, with the same spin, so you are going to get the same factor Vk. And now, when you take the bra, which is also this state, and then you're take the overlap, most of them will give you 0. You will then pick out a factor Vk star. So you can see that expectation value psi g sum over k ck sigma dagger sum over k sigma psi k ck sigma dagger ck sigma. This is going to be 2 times sum over k psi k mod Vk square. Any questions? So go through this calculation, use this form, this notation. It makes the calculation much simpler, and you can show that this is the case for this number operator. This too really comes from sum over sigma. So either you can destroy k up and create k up, you'll get Vk square, or k down, destroy k minus k down and create minus k down, and then again. So this sum over k includes sum over all k, that also includes negative values of k. Similarly, you can calculate this state, psi g sum over kk prime. This is a bit more involved, but you can go through the same steps. So we can calculate this quantity here. Is this me? I think somebody's phone is ringing. So we can calculate this quantity again, and we can write this also in terms of U's and V's. What we'll find is that this quantity is sum over kk prime Vk star UK, UK prime star VK prime. Any questions? So go through this algebra, and now your task is to minimize this expression or set this delta of this expression to 0 and calculate UKs and VKs. Now we know that there is a constraint on UKs and VKs, that is this normalization constraint, that is this. So we can simplify this calculation further by assuming, by parametrizing, so using mod UK square plus mod VK square is 1. We parameterize UK and VK such that UK is sine theta k and VK is cosine theta k. Now this is not the most general parametrization. As you can see, if I write down a phase e to power I phi, this still obeys that equation, that constraint. So in general, you can put another phase here and go through the next few steps. The equations you will calculate, in particular, we will calculate an equation that is called BCS gap equation. There will be no difference at all. So I'm just simplifying the calculation by using this parameterization where I'm dropping this phase. I'm just using this parameterization where UK and VK are real. So this quantity can really be written down as 2 sum over k psi k. Now I have Vk square, so I will have cosine square theta k plus sum over k, k prime sine theta k, cosine theta k sine theta k prime, cosine theta k prime. And there is a vkk prime. So this is the quantity that we need to minimize. So what we will do is, now instead of, so we had two variables UK, VK and a constraint. We parameterized using that. Now we have only one variable theta k. So what we really have to do is del over del theta k double prime, because I've used k and k prime over there. So I really want this quantity to be 0. Now let's do this. Now if you take derivative with theta k double prime, this is sum over k. This would give you only when something finite, when only k is equal to k double prime. So what I will get from the first line is minus 2, or sorry, first term, minus 2 psi k double prime sine 2 theta k double prime. And then this is sum over k, k prime. So you'll get two contribution, one when k is equal to k double prime, and the other one when k prime equal to k double prime. And in both cases, one sum will disappear. Now, these two terms are really same. You can interchange k and k prime and use the fact that vkk prime is equal to vk prime k, because the Fourier transform really just depends on the magnitude of the vector. So finally, you will arrive at this equation: tangent to theta k is equal to sum over k prime So our goal is to solve this equation, and these values of theta k that we'll obtain, using those values we can obtain uk and vk, and that means we would have found the ground state of the superconductor. So it's useful in the discussion of superconductivity to define some new variables, and this will be very useful when we do mean field theory in superconductivity. So what we are going to do is define a quantity delta k as minus half sum over k prime vkk prime sine 2 theta k prime. So this sine 2 theta k prime is really 2 sine theta k prime cosine theta k prime. Sine theta k prime is uk prime, cosine theta k prime is vk prime. So this is also minus sum over k prime vkk prime uk prime vk prime. Now, using this definition, I can write tangent to theta k prime or to theta k as minus delta k over psi k. So I'll just write a few more lines and then we'll continue tomorrow. So this is the equation we want to solve. Now, you see that tangent is negative. Tangent of some angle is negative. That means you can write down sine theta k or sine 2 theta k in this case. We'll choose this to be, which is also 2 uk vk. We'll choose this to be positive. And we'll choose the cosine to be negative. So what have we done? Well, we minimized the pairing Hamiltonian, the Hamiltonian that contains the term relevant for superconductivity, using our variational ground state. The minimization process gave us this equation. Tangent of some angle is negative. That means you have sine and cosine. You have freedom to choose minus sign in either sine or cosine. We will choose the minus sign in cosine. Why have we done this? Let's take the limit when psi k goes to infinity. What does this mean? This means some very large values of momentum, infinitely large values of momentum. What do we expect for those states? We expect that those states will not be occupied. What is the probability that state will be occupied is Vk square. That means if psi k goes to infinity, we expect Vk to vanish. When psi k goes to infinity, you can take the limit. When psi k goes to infinity here, this will give you -1. And on this side, Vk goes to 0, you'll get minus uk square. That means uk square is 1, which is in agreement with our assumptions that uk and Vk are real. If you would have chosen minus sign in sine and positive sign in cosine, this would not be true. So we choose this sign in either sine or cosine, this minus sign, so that we are consistent with our parametrization. So the way I parameterize this is assuming uk and Vk to be real. If you put in some other phase, you might have to choose this sign accordingly. Any questions? So tomorrow, Monday, we'll simplify this problem further. We'll make use of this on-shell approximation and see what that implies for this equation. This questions?